Thank you for watching the video lessons on this my YouTube channel. And I guess the videos are very, very useful to you. Please, I want you to share it, subscribe, and tell others about it. And today's lesson is about the variation of potential energy, kinetic energy, and total energy of a system in simple harmonic motion. How does it vary with displacement and time? So that's what I'll be taking my time to look at to explain in this particular video. Of course, you know that the total energy of a mechanical system is the sum of its potential energy and kinetic energy. Now, the kinetic energy of the body, which is the energy of a body as a result of its motion, is given as half mv squared. And remember that from the simple harmonic equation, the velocity of a body in simple harmonic is given by omega squared, or let's say v squared, omega squared into x naught squared minus x squared. Okay, so that's the expression for the velocity of a body in simple harmonic motion, where x naught, of course, you know, is the amplitude of oscillation and x is the displacement of the body. So I'm going to impute this v squared value in this equation for kinetic energy, and it gives me k equals half m omega squared open bracket x naught squared minus x squared. Okay, so this is expression for the kinetic energy of a body in simple harmonic motion. And you can see that this mass is constant, the angular frequency is constant, the amplitude is constant if there is no loss of energy, which means you can see clearly here that the kinetic energy of the body varies with the displacement x of the body. So at any given displacement between the two extreme positions of oscillations, we can find the kinetic energy. Okay, so let's bear that in mind. Okay, the potential energy of the body is given by half k, say x squared. Now recall again that in spring system, that the angular velocity omega is given as square root of k over m. So if I take square root of both sides, I'm going to have omega squared is equal to k over m. So that my spring constant k is equal to m multiplied by the square of the angular frequency. So I'm going to replace that in the equation for potential energy of the body in simple harmonic motion. That gives me half m omega squared, and then I have the my x squared. So let me call this equation 2. I should have called this equation 1. So these are the two equations. And recall that I said earlier the total energy of a body in simple harmonic motion, the mechanical energy, let me call that ME, is given by the sum of its kinetic energy and its potential energy. So when I add these together, I'm going to have ME equals half m omega squared into x naught squared minus x squared plus half m omega squared x squared. So when we simplify this, of course, we can use this to open this bracket. This times this gives me half m omega squared x naught squared. Then this times it gives me half m omega squared x squared. This is negative now because of negative sign. So this one and this, we cross out this. So what I have here is my total energy, ME, which is mechanical energy, is given as half m omega squared x naught squared. So you can see from this equation that the total energy of a body in a simple harmonic motion oscillation depends solely on the amplitude, because we can keep the mass constant. The mass of a body does not change. In the case of oscillation, the angular velocity of frequency does not change. Of course, you know that angular velocity of frequency is given as 2 pi f. That's what is called angular frequency in radian per second. And the frequency is in Hertz. So this remains constant in the way the body oscillates. And that shows clearly that if I keep all this constant, the total energy ME is directly proportional to the square of the amplitude, okay? Meaning that the total energy ME is equal to K multiplied by X naught squared. Of course, my K. Everything here is my K. That's my constant K. That gives the variation of the total energy with the, amplitude of oscillation. You can see clearly here again that how do we know that oscillation of the body or a body in simple harmonic motion is losing energy? Is clearly seen when the amplitude decreases. And you can see that the variation is not linear. So its total energy varies non-linearly with the amplitude. So if I want to draw a graph quickly of how these two parameters are vary. So I have this is of course so it's equal to k times x naught square. So a graph of that will show that the mechanical energy, which is total energy, against this amplitude will give you a non-linear curve, a parabola that shows that the variation is non-linear. And if I plot a graph of total energy ME against the square of the amplitude, it gives me a straight line graph that starts from the origin. So when the body is oscillating with constant amplitude x naught, it means the body is not losing energy. So we know that the body loses energy or is losing energy when the oscillations are of decreasing amplitude. And you can see how it varies non-linearly, meaning that suppose the amplitude reduced by half. Let's say this is my total energy ME, of course, is equal to k times x naught squared. So if the amplitude reduces by half, I have k x naught over 2 all squared. What happens to the total energy? Let's call that ME1. If I compare these two equations, of course, this is this will give me my initial mechanical energy over my final mechanical energy is equal to this k cancels k. I'm going to have x naught squared over x naught squared over 4. This one cancels, this 4 goes up. So you can see that if the amplitude reduced by half, the total energy, which is ME1, will reduce by a factor of 4. That's what it means. That's the relationship between total energy and the amplitude of oscillation. Okay, so now let's see how these energies, PE, KE, and the total energy, how do these energies vary with displacement? I want to quickly draw a graph here to show how these energies are changing with changing displacement. Okay, so let's say I come here now to draw my axis. So I have here the displacement axis or amplitude. Then on the vertical axis is my energy I'm going to plot. Okay, so let's say I have here the origin, which is zero. That's the equilibrium position of the object in oscillation. Then this is my x naught. That is just like you have something like this. When you have like a pendulum bob now, this is center of oscillation, which is exactly this point. When it swings to this extreme point A, so I can call this my point A. Of course, we say the total displacement or the maximum displacement is called the amplitude x naught. So you can see that when it goes from this point to this point at x naught, that's the amplitude, and it can also swing to the left hand side, of the center of oscillation to another extreme position B, so that the distance from B to the center of oscillation is also x naught. That's the amplitude. I can call that negative because of the fact that the displacement is a vector. And then I come in here and I put my minus x naught. So I'm going to use these 3 points. Or let's say that this point here is my total energy, ME. Or I can use a different symbol, E total or ET. So it depends on the textbook and analysis. Okay, so let's say that let's first start by plotting the kinetic energy, which is given as half m omega squared into x naught squared minus x squared. Okay, when the displacement x is equal to x naught, when you slot out or you replace this, impute x naught for x, that will give me x naught squared minus x naught squared, that is 0. Alright, so it means that the kinetic energy is equal to 0. So I plot here. Then when it's also minus x naught, that is when x is equal to minus x naught, if I impute that in this equation, we need to have positive x naught squared. Alright, so that is x naught squared minus x naught squared, that's also 0. I plot my 0 here, okay? Now, when the displacement x is equal to 0, that is you are the center of oscillation. If we substitute that value in this equation, I'm going to have my Ke is equal to half m omega squared x naught squared, which is the expression for my total energy. So that is what I have here. This place now can be my half m, omega squared x naught squared. I plot there. So with these 3 points, I can draw a sketch, a graph of the variation of my kinetic energy with displacement. Okay. Now then for PE, I have that the potential energy is half m omega squared x squared. So when x is 0, of course, it's very clear here that PE is equal to 0 when x is 0. So I plot here. And then when x is equal to x naught, you see that potential energy becomes equal to the maximum energy, which is the same thing as the total energy, half m omega squared x naught squared, which is the same thing as the total energy me. So I plot here for that. Okay, I can take this point up, take this up because and also take this point up. So what you need to notice is that whether x is equal to x naught or x is equal to minus x naught, when you square a negative number, it's always a positive. So the value of the potential energy remains is. So I'm going to take that out here and plot that against my x naught. Trace this also out and plot that against my minus x naught. So that my graph is looking like this. That is the variation of potential energy with distance. So that my total energy, you can see that when whatever happens, whether x is equal to x naught, total energy remains the same here. Whether x is equal to 0, this is also my total energy. Whether x equals minus x naught, this is still this. So my total energy is just a straight line parallel to the displacement or amplitude axis. Okay, so you can see how the three energy varies. This is my total energy ME, you see. Then this is my kinetic energy Ke, and this is my potential energy Pe. You can see that at some point there where the two energies, the two graphs rather, intercept each other. At such point, at such displacement, the two energies are the same, which corresponds to this point on my energy graph. Okay. You can see that at this particular displacement x or minus x on this other side, the two energies are the same. That is the Ke equals Pe. So they may ask you an examination question, maybe after giving you that the amplitude of oscillation x naught, let's say body oscillation amplitude of 5 cm, they may ask you at what displacement will the kinetic energy of the body equals to its potential energy. So we equate half m omega squared x naught squared minus x squared. We equate that to potential energy half m omega squared x naught, or let's say x squared, not x naught. So if you expand this, you're going to have half m omega squared x naught squared minus half, or I can simply half m omega squared x squared. X squared is equal to half m omega squared x squared. What you can simply do here, these terms will all go out. These and these, they take care of themselves, they cancel out. So what I have left is x naught squared minus x squared is equal to x squared. So I can take each other term together, bring these terms together because I like terms. That gives me 2x squared. So that I have my x squared is equal to x naught squared over 2. Taking square root gives me x naught over square root of 2. Alright, so you can see that if the displacement or the amplitude rather is 5 cm, 5 over root 2 will give me, I just want to show you something there very quickly so that in case you're asked to actually determine that you know what to do, that is at what displacement will the two energies be equal. The displacement is roughly 3.5 centimeter, and that is the point here. That is on the displacement or amplitude axis. At this point of displacement, the two energies are the same. Okay,